In mathematics, especially functional analysis, a normal operator on a complex Hilbert space H is a continuous linear operator N H that commutes with its hermitian adjoint N*, that is, N N** equals N** N. Normal operators are important because the spectral theorem holds for them. The class of normal operators is well understood. Examples of normal operators are unitary operators, N** equals N-1, hermitian operators, N** equals N, skew hermitian operators, N** equals -N, positive operators, N equals for some M. A normal matrix is the matrix expression of a normal operator on the Hilbert space Cn. Properties. Normal operators are characterized by the spectral theorem. A compact normal operator is unitarily diagonalizable. Let T be a bounded operator. The following are equivalent. T is normal. T** is normal. Tx equals T** x for all x. The self-adjoint and anti-self-adjoint parts of T commute. That is, if we write with then, if N is a normal operator, then N and N** have the same kernel and range. Consequently, the range of N is dense if and only if N is injective. Put in another way, the kernel of a normal operator is the orthogonal complement of its range. It follows that the kernel of the operator Nk coincides with that of N for any k. Every generalized eigenvalue of a normal operator is thus genuine. Lambda is an eigenvalue of a normal operator N if and only if its complex conjugate is an eigenvalue of N*. Eigenvectors of a normal operator corresponding to different eigenvalues are orthogonal, and a normal operator stabilizes the orthogonal complement of each of its eigenspaces. This implies the usual spectral theorem. Every normal operator on a finite-dimensional space is diagonalizable by a unitary operator. There is also an infinite-dimensional version of the spectral theorem expressed in terms of projection-valued measures. The residual spectrum of a normal operator is empty. The product of normal operators that commute is again normal. This is non-trivial, but follows directly from Fugel's theorem, which states, if N are normal operators and if A is a bounded linear operator such that, then, the operator norm of a normal operator equals its numerical radius and spectral radius. A normal operator coincides with its Algebra transform. Properties in finite-dimensional case. If a normal operator T on a finite-dimensional real or complex Hilbert space H stabilizes a subspace V, then it also stabilizes its orthogonal complement V. Proof. Let PV be the orthogonal projection onto V. Then the orthogonal projection onto V is 1H minus PV. The fact that T stabilizes V can be expressed as TPV equals 0, or TPV equals PV-TPV. The goal is to show that X equals private equals 0. Since TR is an inner product on the space of endomorphisms of H, it is enough to show that TR equals 0. But first we express XX** in terms of orthogonal projections. Now using properties of the trace and of orthogonal projections we have. The same argument goes through for compact normal operators in infinite-dimensional Hilbert spaces, where one make use of the Hilbert-Schmidt disambiguation needed inner product, defined by TR suitably interpreted. However, for bounded normal operators orthogonal complement to a stable subspace may not be stable. It follows that the Hilbert space cannot be spanned by eigenvectors of such an operator. Consider, for example, the bilateral shift acting on, which is normal, but has no eigenvalues. The invariant subspaces of a shift acting on Hardy space are characterized by Berling's theorem. Normal elements of algebras. The notion of normal operators generalizes to an involutive algebra. An element X of an involutive algebra is said to be normal if XX** equals X**x. Self-adjoint and unitary elements are normal. The most important case is when such an algebra is AC** algebra. Unbounded normal operators. The definition of normal operators naturally generalizes to some class of unbounded operators. Explicitly, a closed operator N is said to be normal if we can write here, the existence of the adjoint N** requires that the domain of N be dense, and the equality includes the assertion that the domain of N** equals that of N N**, which is not necessarily the case in general. Equivalently, normal operators are precisely those for which the spectral theorem still holds for unbounded operators. The proofs work by reduction to bounded operators. Generalization. The success of the theory of normal operators led to several attempts for generalization by weakening the commutativity requirement. Classes of operators that include normal operators are quasi-normal operators, subnormal operators, hypernormal operators, paranormal operators, normaloids,